Hey everyone, and welcome to this explainer. I am absolutely thrilled to get into this topic with you today because we are going to build a complete whiteboard-style toolkit for you to totally master IGCSE physics properties of waves. If you're a focused learner looking to really grasp these concepts directly, whether you're seeing this for the very first time or you're cramming for that major exam, you are in exactly the right place. So let's just jump right in.
Here is our quick game plan for the session. We'll start with transverse and longitudinal waves. Then, the anatomy of waves, followed by compressions and rarefactions. After that, we'll tackle the wave speed equation, wavefronts and direction, and finally, wrap it all up with the reflection of wavefronts.
All right, Section 1, Transverse and Longitudinal Waves. Let's look at the types of waves.
Okay, so the absolute bedrock idea you need to internalize here is that all waves transfer energy from one place to another without actually transferring matter. But how they do that? Well, that falls into two main categories. Let's start with a transverse wave. A transverse wave is a wave where the particles of the medium vibrate perpendicular to the direction of wave travel. Now, the absolutely crucial point here is that word perpendicular. Examiners are quite literally scanning your exam paper for that exact word when they ask for a definition. Things like light waves, UV waves, water waves, and seismic S waves, these are all prime examples of transverse waves.
To really visually anchor this, take a look at the diagram. Notice how the blue line represents displacement. As the wave's energy travels forward, moving from left to right across the screen, the actual particles of the medium are just bobbing up and down. That perpendicular up and down particle motion is exactly what creates those high points, which we call crests, and the low points, which we call troughs.
Now let's pivot over to our second type. A longitudinal wave is a wave where the particles vibrate parallel to the direction of wave travel. For this one, I need you to heavily emphasize the word parallel in your mind. It is the absolute crucial differentiator from transverse waves. Sound waves and seismic P waves are your classic go-to examples for this wave type. Let's connect that definition right to the visual. Because the particles here are vibrating parallel to the energy transfer, meaning they're really just shuffling back and forth in the exact same direction the wave itself is moving, we don't get those physical peaks and valleys. Instead, this parallel vibration creates bunched-up regions, which we call compressions, and spread-out regions, which are called rarefactions.
Seeing these two waves side by side really brilliantly illustrates the difference, doesn't it? On the top, you've got the longitudinal wave, with its back and forth parallel particle vibration creating those compressions, and on the bottom, the transverse wave, with its up and down perpendicular vibration creating crests and troughs. Seeing them together like this really cements the difference between the direction the energy is transferring and the direction the individual particles are actually vibrating.
To wrap up this foundational concept, here's a classic IGCSE checkpoint summary table. Honestly, take a mental snapshot of this right now, because examiners frequently ask you to reproduce this exact table of differences. Remember, transverse is perpendicular, features crests and troughs, and includes light waves. Longitudinal is parallel, features compressions and rarefactions, and includes sound waves. Got it? Awesome.
Moving on to Section 2, the anatomy of waves. Time to look at the measurable parts. Now that we understand the two main types of waves, let's look at their measurable parts. Looking at the red and blue labels on the screen, notice that horizontal black line slicing straight through the middle? That's the rest position. It's exactly where the medium would sit if there was zero wave energy passing through. By establishing this rest line, the diagram gives us the physical starting point necessary to measure exactly how much energy the wave carries and how long a single wave cycle actually is.
Let's formally define those measurements. Amplitude is the maximum displacement of a wave particle from its rest position. Wavelength is the distance between two consecutive points in phase, like measuring from one crest directly to the next crest. Now listen closely because I have to warn you about a classic exam mistake. A lot of students try to measure amplitude all the way from the very bottom of the trough to the top of the crest. Do not do that. Amplitude is always measured correctly from that flat middle rest line up to the crest or down to the trough.
Section 3. Compressions and rarefactions. Let's get into the longitudinal details. Okay, pay close attention here because this is a notorious area for student confusion. Notice how the physical sound wave at the bottom is perfectly aligned with the transverse graph at the top? I'm showing you this setup to expose a huge exam trap. Sound waves do not actually have physical crests and troughs. They only have high-pressure, dense compressions and low-pressure, spread-out rarefactions. That wavy blue line on top, that's just a mathematical graph representing the changes in pressure. Never, ever draw a sound wave in an exam as a literal squiggly ocean wave.
Section 4, the wave speed equation. This is the holy grail formula.
Here it is, the absolute holy grail formula for this entire topic. V is equal to F times lambda. Let's clearly define these variables and their standard IGCSE units so you're ready for the math. V is the wave speed, measured in meters per second. F is the frequency, which is honestly just how many complete waves pass a specific point every single second, and that's measured in hertz. And finally, that Greek letter lambda represents the wavelength, which is measured in meters.
All right, let's transform this from passive viewing into some active problem solving. Here is a super standard exam calculation question. A wave has a frequency of 50 hertz and a wavelength of 4 meters. Find its speed. Take a second. Think about exactly how you would set up your page to solve this to get maximum marks.
Here's the logical breakdown of exactly how you should answer this. Step 1. Always write your working formula, V equals F lambda. Step 2. Plug in your numbers, so 50 times 4. Step 3. Solve it to get your final answer of 200 meters per second. I remind students constantly about this. Writing that formula down in Step 1 is exactly how you secure partial marks, even if you accidentally make a silly calculator error later on. Always show your work.
Section 5, wavefronts and direction. Taking a macroscopic view.
Shifting gears to the macroscopic view, imagine dropping a stone into a ripple tank. Notice the circular wavefronts expanding outward. The dashed circles are the wavefronts. They're basically lines joining points on the wave that are in the exact same phase, kind of like mapping out all the crests from above. But point your eyes to the red rays pointing outward. The crucial geometric relationship you absolutely need to memorize here is that the rays showing the direction of travel are always exactly perpendicular to the wavefronts. It is always a perfect 90-degree angle.
And finally, Section 6, reflection of wavefronts. This is the final boss of the topic. Applying the law of reflection to complex wavefront diagrams is a highly weighted exam skill, so let's nail it. When you are asked to draw a reflection diagram, here are the exact procedural steps you must take with your ruler and protractor. Step 1. Mark the normal line perpendicular to the boundary. Step 2. Measure the angle of incidence between the incoming wave's direction and the normal. Step 3. Draw the reflected wave at the exact same angle on the other side. But critically, and do not forget this, you must ensure the spacing between your drawn wavefronts remains exactly equal to the incoming ones.
What's really fascinating here is seeing how that rule applies in practice. Look at the incoming vertical blue lines on the left side of the diagram. Those are straight incident wavefronts. They hit that diagonal flat barrier and reflects straight downward. Notice how the reflected horizontal blue lines maintain the exact same gap spacing as the incoming ones. That is because frequency, wavelength, and wave speed simply do not change during reflection. The spacing literally has to stay identical.
Let's see how this applies to circular sources hitting a flat barrier. Guess what? The exact same law of reflection applies to every single point. Notice how the reflected arcs bounce back following those red arrows. I know it looks complex, but it's really just geometry. It creates a pattern as if an identical phantom wave source was placed at the exact same distance behind the barrier. Pretty cool, right?
We've covered a ton today. The definitions, the math, and the drawing skills. But to wrap up our explainer, I want to leave you with a provocative question to really test your fundamental understanding. If reflection doesn't change a wave's speed, frequency, or wavelength, what real-world technologies rely entirely on this perfectly predictable bounce? Think about ultrasound imaging in hospitals, radar systems tracking flights, or sonar mapping the deep ocean floor. Physics isn't just formulas on a whiteboard, it's literally everywhere around us. Thank you so much for learning with me today. Keep reviewing these slides, and I promise you, you are going to be brilliantly prepared. Catch you next time.